Hi, everybody. We'll continue to talk, and now we are in a different subject. This is about logic. All right. So hopefully it makes sense, right? Because it's just logic, but it can be complicated as well. The foundation of math, argument and computing. This idea was introduced many years ago, like 350 BC. I think Aristotle started it. So for centuries, this principle has formed the basis for systematic thought, communication, and debate, and law and math. So there is many applications for it. And we say we have a declarative statement that is either true or false. So let's say it correctly. A statement is a declarative sentence that is either true or false. So, for example, George Washington was the first president of the United States, right? George Washington was the first president, right, of United States. That's a statement that is declarative, that is either true or false, right? Orlando Magic won the NBA championship of this, something like that. The number of atoms in the universe is 10 power, let's say the number of atoms in universe as this, so these are statements. If you want one, do your homework. That's another one. That's another statement, right? But you say, okay, that's a good idea or not. Let's just do this. Here is a statement, right? So it's fun. So if we talk about these, of course, you're gonna say whether now kind of a test, right? The first one, George Washington is the first president of United States. Is this a declarative statement, right, or sentence? Yes, it is. Is it true or false? Right? Yes, it's true. If it is true, is it a statement? Yes, it's a statement. Let's call this DS and this just S. All right. So you see, now we're using the logic, right? So George Washington is the first president. So yes, it's a declarative sentence because it's either true or false. And in this case, it's true. And because this definition is met, we can say yes, it's a S, which is a statement. And you can follow the others. All right, so what do you think about number 2? Did we count how many atoms are in the universe? No. So is it DS? Yes, right? It is false, right? But it's still a statement, right? All right, number 3. Yeah, it's DS. You see, the problem with this, neither the value of X is not specified, all right? So you can say this is true. You can say this is false. Why? Because this can be solved, right? It clearly can be solved. you do 2x minus x equal x, x equal 3. But it's not as a statement, right? It's neither true or false. We don't know because x is not specified. So it's not a statement, all right? So this is the first thing that we need to know. And then after, we need to work on some symbols. In this thing, we use conjunction. When we use and, this is the symbol for it. This junction is with this symbol, and it means or. And negation is we use this symbol, and it means not. All right. And of course, if we use this symbol, it means it is not the case that P. All right, so if you see this symbol, it means it is not the case of P. So conjunction means and, this junction means or, and this is looking up. And negation is this symbol, which is not. And if you see P, it means it is not in the case of that. And we have a problem with this not coming down. Here it is. All right, so maybe we talk about some example. So let P denote a statement. So let's P denote a statement that Anna here likes popcorn. That should be true, right? And Q denote the statement Fred likes peanuts. That's tricky because peanuts are tricky, not like popcorn. So let's write with logic way some statements. So you'll see how instead saying Anna likes popcorn and Fred likes peanuts, I can just do this. So you see how it turned to math. So, and if I want to say Anna likes popcorn or Fred likes peanuts, it's going to be opening up. And if I say Anna does not like popcorn, then I will do this. All right. So we can do more examples, but we can talk about this. And of course, there is a few things that, you can combine, so I'll give you this question and think about it. So what if it says, for example, this? What does it mean, right? Or let's just make it simple. Something like this, right? So it is stuff to think about, and you see that statements can be changed to math, and math notation, make it simple. So the implication here, this symbol represents the English connective, if, then, all right? So if you see this, and this is used in many coding algorithms when you see things, this arrow here stands for if, then, in that the symbolic statements, P, arrow Q, then reads FP, then Q, all right? All right, so let's do some other examples so we understand a little bit more of this. Then we talk about truth the truth tables. Let's say, let's denote the statement W. You know, it doesn't mean that P and Q have to be used all the time. So let's say W, a statement says the train stops in Washington. Train stops in Washington, right? And let N denote the statement train stops in New York. All right. So let's write the train stops in New York and Washington, right? So should be no problem. But let's look here. I'll just point to something. I say the train stops in New York and Washington. So let's do it this way, just to make sure. All right, the train stops in Washington, but not in New York. It stops in Washington, but not in New York. You see? So now it helps you reflect now on the others. The train does not stop in Washington. All right? The train stops in New York or Washington. You know, then you can have more things. The train stops in New York or Washington, but not in both. So this one I need to write because it's a new one and it's interesting, so we understand this. Train stops in Washington, in New York. It's in New York. In New York or Washington. Yeah, so it stops in this one or that one, but not in both. All right. So it stops in New York or Washington, right? That's the first one. But not in both. So we need to use and because we need to, as I mentioned, conjunction thing, because this statement has a conjunction with the first one. So, and now there is something follows that says, but not in both, which means not in New York and Washington, right? So you see, not in both, so not in both, it doesn't mean or, it means in this one and that one, right? So that's how the statement is written. So meaning, if you read the math, you can say the train stops in New York or Washington, but the train does not stop in New York and Washington, right? All right. So we use, just like we usually use in parentheses in math, this makes it super clear, these parentheses here. So let's look at another example. If the train stops in New York, then it does not stop in Washington. You see, if it stops here, it doesn't stop there, right? If train stops in New York, then it does not stop in Washington, right? So what do we need to do? Look, all this sentence, we can just do this. That's it. If it stops in New York, then it does not stop in Washington. All right. So you can try some more of these examples. It's very interesting. You see the power of math here. Thank you. We'll continue on another video.